Welcome, everyone. For today's prep, we're going to start looking at power series. So we'll see what the definition is, and we'll look at a nice, easy example. And ultimately, what we're going to be doing in this set of notes is we're going to see how to find the radius of convergence and the interval of convergence for a power series. And we'll see that both of these are really related to, if we view the power series as a function, both of these are related to the domain of our function. All right, so what's the definition? How are we defining power series? So it's a power series of, well, this is kind of a more specific form. It's the sum from n equals 0 to infinity of c sub n times x raised to the power n. So now we're starting to incorporate some variables in our series here. And so x here is the variable. So when we talk about a power series, these values for c, these c values here, we're going to call these the coefficients. And x, well, just as we expect, x is going to be our variable. And we don't have to use x, but that's, generally the variable we're going to be using. And so if we were to write this first version of our power series out, when n is equal to 0, well, that would give us c sub 0 times x raised to the power 0. So we're going to be using the convention that x raised to the 0 is just going to be equal to 1. So just to kind of note that. Then, when n is equal to 1, our next term is going to be c sub 1, so the coefficient of the n equals 1 term, and then x raised to the power 1. So you can think of c sub 1 as the power coefficient of the linear term. You can think of c sub 2 as the coefficient of the squared term. You can think of c sub 3 as the coefficient of the cubed term. And this just kind of keeps going on like this. And again, with a series, we're trying to add all these terms together. All right, so that's if we write out the first few terms of a power series. This is our sigma notation. Now, this is really a power series that's centered at 0. So this is kind of a special case. So this is really a power series centered at a equals 0. More generally, we can have a power series that's centered at some other number, which we'll just kind of leave as just a. And it has the same kind of formula here. So we're going to be doing a sum from n equals 0 to infinity. We still have our coefficient term, so c sub n. But then rather than x raised to the power n, we're going to have x minus a raised to the power n. So really what we have in this power series is we have powers of x minus a. So, we still have the constant term. So with exponent 0, we still have the linear term with exponent 1. We still have the squared term with exponent 2, and the cubed term, and so on. And you can still think of c sub, say like c sub 3, still the coefficient of the cubed term. C sub 2, still the coefficient of the squared term, and so on. And again, we're going to be using the convention that x minus a raised to the 0 power is 1 as well. Okay, so this is a power series, and we can write out the first few terms. Helpful to do that. We can also write it out in sigma notation like this. And the question is, when we have a power series, we can write it down, no problem, but does it actually represent a function? And that's going to be kind of a fundamental question we're going to be looking at over the next bunch of sections here. And we want to investigate if we have this power series, we can think of it as a function, and then the natural question is, well, what is the domain of this function? And it turns out that, we've all the talk about series and series tests that we've been doing is going to give us a way to determine this domain. So we say that a number x is in the domain of this function if the resulting series converges, and a number x is not in the domain if the series diverges when we plug in that x value. So to give a little example, we're going to look at example 1 here. So a nice simple power series. So it's the sum from n equals 0 to infinity of x raised to the power n. And we're ultimately going to figure out the domain of this function. But first, let's evaluate this function when x is equal to 1/2. Okay, so let's try that out. So let's start with x equal to 1/2. Let's do our evaluation first. All right. So we're going to take 1/2, and wherever I see an x in this formula, I'm just going to, just do what we normally do, plug in 1/2. And when we do that, we get the sum from n equals 0 to infinity of 1/2 raised to the power n. Now, this is, we've seen things like this before. This is a geometric series. So this is a geometric series. And if we remember the general form for a geometric series, it looks something like this. So it's the sum from n equals 0 to infinity of a times r raised to the power n. This is a geometric series. And in our case, for this power series that we're looking at with this evaluation, the a value, and just to mention, the center of the power series, this a value, is different from just this a value when we're talking about general geometric series, just to make that distinction. But this is a geometric series, and the a value here is equal to 1, and the r value here is equal to 1/2. So we know that when the r value is, the absolute value of the r value is less than 1, our series converges. So this is a convergent geometric series. The a value is 1, the r value is 1/2, and so we can figure out what the sum actually is. So the sum for a geometric series is a over 1 minus r, and if we fill in our values, it's 1 over 1 minus 1/2, which simplifies to 2. So we can actually say what the value of this function is, what the value of this power series is at x equals 1/2. The value's 2. All right, so the fact that when we plugged x equals 1/2 in to this power series and we got something out that was convergent, that means x equal to 1/2 is in the domain. So now let's figure out what the domain is precisely. So again, we want to know, where does this power series, for what x values does this series converge? And we know that for a geometric series like this converges when the absolute value of r is less than 1. And it diverges when, the absolute value of r is greater than or equal to 1. So the domain of this power series is wherever this thing converges. So rather than plugging in 1/2, let's kind of look at this general form. So our function f of x, which is written as the sum from n equals 0 to infinity of x raised to the power n, this is a geometric series. The a value is still 1. That's just the number in front of the kind of the r value here. And the r value is x. So I'm just trying to match up the general form for a geometric series like this with the formula for our power series. So I see that I have x raised to the power n that matches up with r raised to the power n. So if we're viewing this as a geometric series, the r value here is just x. And we know that this converges when the absolute value of r is less than 1. So that means it converges when the absolute value of x is less than 1. And that's, well, this kind of describes our domain. So we're going to write this as an interval. So we can say that this converges when x is in the interval from -1 to +1. So this absolute value inequality, so absolute value of x being less than 1, is equivalent to this interval here. And this is the domain. So we have our, well, we got our domain. It's all the numbers when x is between -1 and +1. So a way to kind of see where you'd get this interval from is when we have an inequality like this, we can rewrite it, put the x in the middle, get rid of the absolute value, and or whatever term is inside the absolute value, you kind of keep in the middle, and then you keep the number over here on the right, which was 1, and then on the other side, we make this into a double inequality, and we put the negative version of this number, so -1 on the other side. And then from there, we can see that that's the interval. All right, so in class, we're going to keep investigating these types of power series, and we're going to see how to do this more generally for power series that have more unique coefficients, not necessarily just a coefficient of 1. So we'll see you then. Bye-bye.